Hi, Mark Palmquist here. It appears like a lot of people are interested in the video that I posted about how the shape of a boat affects its speed at different speed ranges, and how some boats have a ideal speed range which is low and some have a speed range that is high. And because I do all of my videos stream of consciousness, I don't have a script. I always leave things out that I wanted to include. So let's jump right in. I'm doing part number 2, and I'm going to do some more three-dimensional type sketching. Talk a little bit more about water pressure, waves, wave formation, and how to minimize the creation of waves. All right, before I jump into the 3D drawings, I'm going to go back to the 2D and explain a couple things about these shapes. These shapes are really good for having low drag at low speeds. They're not really good at having low drag at higher speeds. So this is a canoe. It's powered by paddles. What happens to the water when it hits here? The water hits this wall, and some goes up, some goes down, and some goes sideways, and then some of it goes under the boat like this. So it goes this way, and then it gets deflected slightly, and then most of it goes under, and then when it gets to the back end, it's the opposite. It's kind of drawn this way, and then it pops out over here. So at low speeds, a lot, and then the water that's hitting here, most of it just goes around the side. At low speeds, this is not a problem, but as you're going faster, as you increase your speed, more water is getting drawn under the boat here, and when it leaves, it's lifting around this curve, because a canoe has a curved bilge. So what happens is the bow starts going up in the air, and the stern starts being sucked downward because of the water that's exiting is being lifted around the curve. There's not a sharp edge that allows the water to keep going the direction it wants to go. It lifts the water. So, okay, so here's a side view of a canoe. Some water goes up and creates a little wave, and then some water gets deflected downward, goes under, and then pops back up and shoots out this way. And because water is sticky, and it's the Coanda effect, water is going to lift a little bit here, and this creates the stern wave. And at low speeds, these waves are very small. But once you get into the medium range, where you're shifting from into more dynamic forces, so static would be 0 to 5 knots, and then the mid-range, where you're transitioning into dynamic lift, is, I would say, about 5 to 8 knots. That's where dynamic forces start becoming a major factor. Okay, so what happens is water is lifting, so it's going to push or suck the back of the boat down, and eventually you get something like this. Now, if this angle gets above 4 degrees, then then it becomes inefficient. So you don't want to go above 4 degrees. If you hit 4 degrees, then you're good. That's actually an ideal angle for lifting a hull out of the water, is 4 degrees. But because of this long area, basically from the mid all the way to here, this is all sucking the boat down. So again, that's why when the fin designer cut the back of the boat off, he created a faster boat. So how can you shorten the length of a boat and make it faster? That doesn't make any sense. But it was a long canoe, and so when he cut the back end off, hold on. So it was a really big canoe, and when he cut the back end off, what it did was it moved the widest part of the boat slightly behind the midpoint. So now this is like 60%, and this is 40% or something like that. And you have more of the boat that's lifting in the front, and you have less downward sucking in the back. And this creates a really good medium speed shape. Okay, another reason that this boat shape became faster than this, which was the traditional shape, where the widest part of this boat is slightly ahead of the middle. So that's the way the old boats were. The widest part was slightly in front of middle. So this might be, you know, 45%, and this might be 55%. So so this boat beat out that boat. Boat designers that were involved in racing kept moving. They kept experimenting, and basically they kept moving the widest part of the boat back, and kept making this angle smaller at the nose, and this minimized drag, and the boats became faster. The 49er skiff is a good example of a boat like this. So that is why this boat is even faster than this. So it goes, this is slow, this is like medium, and this is fast. I didn't really talk about why this wide transom is an advantage, and I'll explain it to you in the side view. Okay, here's a traditional shape of a boat. We had a Cape Dory Typhoon, and it looked very much like this. This boat has a keel, so it's very stable, it's seaworthy, but it does have this deep curvature, and it's heavy. So modern boats are becoming less deep, and they're becoming lighter, and they're becoming wider at the stern. So this boat has a speed limit, and you've probably heard the speed limit. It's length, water, line, square root of that times 1.34. So if you measure this length here, take the square root, multiply it by 1.34, that gives you the speed limit of a boat like this. This speed limit does not apply to boats that are relatively flat on the bottom and light, because boats that are flat and light can get above the speed limit because they can hydroplane. A boat like this can never hydroplane. It just has too much rocker. So this boat is ideal for low speed conditions, but it's not going to go fast if the wind picks up. It's basically going to hit its top speed at about less than 10 knots of wind. And it's not like the Cape Dory Typhoon, it never went above 5.5 knots. Okay, so this is the shape of a modern skiff. Looks like something like this. It has this kind of shape in the back, and then it gets a little bit more vertical here, and then it comes to a point. And so this boat takes advantage of, so a boat like this, when it's going slow, it doesn't heel, so it has this long water line. The very tip here is under the water, and so it has a long water line. When you get into the dynamic speed range, length water line becomes less important. So when this boat starts to heel, its water line will shrink, and it will get more like this. The wetted area will be like here. And the best shape for for a wetted area is a teardrop that's like going backwards. So the widest part of this teardrop is slightly behind the middle. And this shape is the ideal shape for a submerged waterline. And a lot of this has to do with waves. If you didn't have to deal with waves, it would be the opposite. It would be more like a airfoil shape where the fattest part would be in the front. But because you're dealing with breaking down waves, it's advantageous to flip it around and have a reverse teardrop shape. So let's look at the heeled boat shape. It's more like this. And again, there's more of the front of the boat is out of the water, but you got this nice flat section in the back that's hydroplaning. And it's so the advantage of when you make the stern really wide, what it means is you can minimize the rocker. So you get this nice shallow wide dish over here, and that's the wetted area of the boat. And it's better to have a shallow wide dish when you're going above, when you're beginning to break into the dynamic speed range, than it is to have a long water line. So let's look at this elliptical stand-up paddleboard. Is this the ideal shape for a paddleboard? The answer is no, it never is. An ellipse is the wrong shape for a stand-up paddleboard. However, some people take these in the ocean and they surf waves. And so in that case, it would be an ideal shape. So in other words, this shape is kind of a compromise. I guess the elliptical shape is intended to, it's not the fastest shape for if you're just paddling on a lake, but if you take it to the ocean, this is going to be very fast, and you'll be able to ride waves with it. All right, let's look at water hitting a plate. Let's just imagine a wall, and imagine this is a perpendicular line. If you have a hose, a high pressure hose, and you squirt water, the water will radiate in all directions equally, forming a circle. And it will stay tight to the wall. If you change the angle and you're coming, let's say you're standing back here and you're going this way, it changes shape. So now most of the water goes shooting, it's more like an ellipse, and only a small amount of water goes backwards and most of it goes forwards. And you can keep changing the angle so that this angle with the wall becomes very small, and then all the water is squirting this way and just almost nothing is going backwards. This is how you minimize pressure. You just keep on changing the angle, making the angle smaller, and that minimizes pressure. So let's say you had a boat and it had to be a certain width and it had to be a certain length. And let's say you wanted this to be a lightweight boat and you wanted it to go fast. One thing that you could do to make it go faster is you can do this with the angle. You minimize the angle here. And then here you can accelerate the curve, and then you can have some angle here. So this is basically what has happened with the shape of a skiff. Is this area here has been eliminated, and now the waves hit, and the wave amplitude is lower because the angle is not as severe. So you're basically just moving the middle of the boat backwards. And that's why boats have evolved this way. It has to do with this angle of incidence. This is going to create a steeper angle than that with the oncoming water. Okay, let's look at speedboats. There's a boat called the John boat. It's basically a rectangle, and the sides go like this, they're flat, and then they go up like this. So now you can imagine a boat like this is going to be really inefficient at low speeds, but it can hydroplane, and if you go above 8 to 10 knots, this boat will be extremely efficient. The only issue with a flat bottom boat like this is, hitting waves. So let's look at, here's a John boat. Looks like this. And most speedboats are like this. This is a typical speedboat. It has a shallow V. And it turns out that you can add a 10-degree dead rise here without losing too much of your lift. So that's why most boats nowadays, they have between 10 and 15 degrees of dead rise. The boats that go in the bigger waves usually have 15, and the boats that go on lakes usually have 10 or closer to that range. And you can do it up to a point before you start losing your lift. And so it's almost like getting more comfort for free. Most things that you do in changing the shape of a boat, there's always something that you lose. If you do something, there's always something you gain and something you lose. And in this case, you can gain comfort because you're not smashing into the waves as heavily, and you don't lose too much of your lift because the water is no longer being, on this boat, the water is being directed downward. And over here, it starts being directed sideways. And so it's kind of hard to illustrate this three-dimensionally, but I'm sure you can imagine. Okay, so the other thing that's shaped like this is a swamp boat. Swamps don't have any waves because they have grass, and the grass, there's no waves. So the ideal proportion of a boat like this is about 1 to 2. You look at the proportions of a swamp boat, and if it's 4 foot wide, it's 8 foot long. If it's 6 foot wide, it's 12 foot long. So they usually go with an aspect ratio of 0.5. All right, so what about a stepped hull? What is the purpose of a stepped hull? Let's go back to drawing a speedboat. Speedboat. Speedboat looks like that. When the speedboat is going slow, the transom is under the water. Looks like this. This is a speedboat at rest. When the speedboat is going fast, it looks like this. And the underwater area becomes a delta shape like this. So that is the only thing that's wet, is this shape right here. When a speedboat is going fast, is this basically a delta wing shape. So this reduces surface area, and and it reduces drag. And this is a fully hydroplaning boat. Now, one thing that you can do is you can add steps in the hull. So like a step looks like this, goes like this, and then it goes like that. It goes like that. And I've read a lot of research papers, and I've discovered that when you add steps, this doesn't really help unless you get above a Freud number of 3. So a Freud number of 3 means you're going 3 times faster than its speed limit. So in other words, if you take the length water line, you take the square root of that and you multiply it by 1.34, and then you take that number and multiply it by 3, that is the speed at which a boat like this would have an advantage over a boat that didn't have any steps. So what the steps do is it creates multiple wetted areas that are a bit higher aspect ratio. So instead of having something, here, let me draw over here. So then you get wetted areas that look like this as opposed to one that looks like this. So you're increasing the aspect ratio of the wetted area when you have a step, and you're minimizing the entire total wetted area of the boat that doesn't have a step. Okay, here's one more quick video. Catamaran. Speedboat. How come speedboats aren't catamarans? I mean, catamarans make really fast sailboats, right? Well, the answer is this is fast in a medium speed range, but if you stick a motor on a motorboat, you can get up to 40, 50 miles an hour. You can't do that with a boat like this. This boat has an ideal speed range between, I would say, 15 to 25 knots at the most. And I've watched videos when people have put, like, for instance, a motor on a catamaran, and they don't go very fast. So this is an ideal shape for low to medium speeds, and this is an ideal shape for high speeds. The length to width ratio is very different than this one. This is, 12 to 15, and this one is more like 3 to 1. So if this boat was going slow, would it be efficient? The answer is this boat is extremely inefficient anywhere near its hump speed. So a motorboat that has a motor and it has this shape, its ideal speed range is going to be either super slow or super fast, but it's not going to be anywhere anything near the hump speed. It's going to be extremely inefficient. And then the efficiency will go up as you pass over the hump speed and continue to pass the hump speed. Right, so in conclusion, for a rowboat, it is now discovered that a boat like this, that is basically a long, narrow boat, but it has a flat transom, is going to be faster than a boat like this. And the guy Sam Manuar, I guess it's Sam Manuar, the guy who designed this rowboat called the Light Boat, is he designs boats, sailboats that go really fast. And so he understands this principle that if you go over a certain speed range, having a squared off transom is actually an improvement. And the people that designed these boats, they didn't realize that. So if I was going to design a rowboat that was going to be for racing, and I knew that it could go over 8 knots, I would design it like this.